Welcome back. Today we're going to discuss some fundamental key concepts from graph theory. In the last lecture, we overviewed consensus and synchronization problems. So if you haven't watched last lecture, please watch before this one. If you already have an understanding, a preliminary understanding of multi-agent systems or graph theory, you can just start from this video. Anyhow, so in the last video, we looked at the consensus problem with two agents and synchronization problem when not only information exchange between vehicles depend on each other, but also some external inputs. Command C is applied to the multi-agent system and makes this agent leader since it knows the command. And if you look at here, they just exchange the information. And we modeled that information in state space. If you can write x1 dot, x2 dot into the vector form, then this is what you are going to get. Minus sign, I intentionally put it here, minus x1, minus plus x2, so capturing this equation, likewise the second equation. And when you have additional inputs, in addition to this nominal baseline portion, which we have a matrix called Laplacian in both examples, which is a very important matrix in control of multi-agent systems. We will get to it in detail this lecture. And because of leader-follower algorithms, we have some additional items here. X1 minus X1 plus C coming from this part. All right, so either consensus or synchronization agents or vertices, nodes, node 1 and node 2 in this case, is a part of a graph. And another element that is part of a graph is the edge, which captures the connection. This solid line is the edge or connection. And again, this is the vertex or node of agent. And we are going to look at agents having, not just two, but n number of agents. And so the vertex set contains all these agents, and an edge set contains vertices multiplied by vertices. These agents exchange information with each other. So mathematically speaking, an edge ij means that there is a connection from vertex I to vertex j. Now, some books in engineering, some books in graph theory um, has the same definition, but some books change the arrow from here to there. Throughout this lecture, I will be more intuitively consistent with myself and these slides. An edge means that, agent I sends an information to agent J. Think about like this. This command is sent to agent 1. So agent 1 is driven by another minus x1 minus c type of a edge, directed edge. And graphs can be undirected or directed graphs. In undirected graphs, we discussed a little bit in the last lecture. There are, both agents. Agent I sends information to agent J. Likewise, agent J sends information to agent I. But instead of using these two arrow notation, we just draw a solid line. Whenever you have a solid line, it means agent I and J both sense information in each other. It means that mathematically, if Ij belongs to this edge set, this implies also there is an information from coming from J to I for undirected graphs. For directed graphs, however, if, for example, I sends information to agent J, it does not necessarily imply agent J also sends information to agent I. In this case, we have to put an arrow. Solid line means that they both sense information, and in this case, just agent I sends information to agent J. So it is a directed arrow. So these type of graphs called directed graphs. So in addition to graph types, there is a matrix called adjacency. Adjacency matrix is a simple matrix. I will do an example. I will do two examples immediately in the next two slides. So basically, Aij is 1 if there is an edge from I to J, some information. Otherwise, it is 0. So like in this example, both agents sense information. I'm gonna write the agents matrix. I'm looking at I and J. This is I and J. Since agent 1 receives information from agent 2, there is 1. Likewise, since agent 2 receives information from agent 1, there is a 1 here on the adjacency matrix. So A is 0, 1, 1, 0. I just showed it here because I will use in an example. These adjacency basically off-diagonal terms capturing whom an agent receives information from what other agents. And degree matrix is basically summation of all the AJs. For example, here, if you look at this adjacency matrix, it is 0 plus 1. Degree is the diagonal diagonal elements, so it becomes 1. Likewise here, it becomes 1. But, in this notation, you can produce Laplacian as you compute degree matrix, you have adjacency matrix, sum them up with the D minus A will give you the Laplacian matrix, which is 1 minus 1 minus 1, 1, which we used in these two examples since the agents exchange information over the undirected graph. This Laplacian matrix pops up, which is once you have degree and adjacency, you can compute L. Let's do an example, okay? Enough with the theory. So this is an undirected graph because all agents, there are no arrow indications. So agent 1, agent 2 exchange both information with each other, likewise 2 and 4, 2 and 3, and 4 and 3. So in this case, we have and 2, 3, 4 edges. You can have certainly more edges than nodes. Simply, if you can put an edge between 1 and 3, you will have 5 more than number of agents. And likewise, you could put 1 to 4. Anyway, so I like writing the Laplacian matrices not like D minus A, but I just compute everything like this. For example, I look at agent 1. Agent 1 receives information from agent 2. So I need to put a minus 1 here. Agent 1 receives information from no information from 3, no information from 4, just from 2. That's it. Then summation of these minus 1s, which is coming from D minus A, that's why adjacency comes with minus sign, this D minus A. But again, you can view this as a whole, the Laplacian matrix, you can directly write it, just diagonal terms degree. Agent 1 is only connected to agent 2, so my degree is 1. Now, looking at agent 2, agent 2 is connected to 1, 3, and 4, 3 agents. So for its degree, this is a 2 by 2 term, I put 3. Likewise, agent 3 is connected to 2 and 4. So this third entry of this 3-row and column entry is 2 because agent 3 has 2 degree. Likewise, 4 is only connected to 2 and 3. So I initially write degrees, just the diagonal terms, looking by how many neighbors I have, from how many neighbors I receive information, and then minus 1. Now I look at off diagonal terms for agent 2. Agent 2 receives information from 1, 3, and 4. So 1, 3, and 4. Likewise, look at agent 3. It receives information from 2 and 4. So minus 1 and minus 1 to 2 and 4. The remaining is 0. Likewise, the fourth agent receives information from 2 and 3, minus 1, minus 1 comes here. So this is how we generate undirected and directed matrices. And I will do a directed example in the next slide as well. But I would like to mention a fact which is very important. In general, for undirected and connected graphs like this one, always Laplacian matrix becomes symmetric, meaning L equals to L transpose. In other words, this row is similar to this row, same as this row. This row same as this column same as this row, or simply L equals to L transpose for undirected. Don't forget undirected and connected graphs. And for those graphs, there is, Laplacian matrix has 1, 0 eigenvalue, because if you can find uh, uh, linearly dependent columns and rows of one. And this zero metric, the zero eigenvalue of the Laplacian is only one, and it corresponds to the null space or the eigenvector of 1, 1, 1, 1, 1. And you may remember this from previous lectures. And we look at the second smallest eigenvalue because second smallest eigenvalue will be always a positive one, and it captures convergence. We're gonna do examples. It is called algebraic connectivity. Some references, or in myself, I would like to call it as the Fiedler eigenvalue. You can also call it algebraic connectivity, but I like Fiedler eigenvalue better. We look at the second eigenvalue, especially for the consensus type problems, since the first agent is eigenvalue is zero, meaning that, you know, if I construct some dynamics based on this, like this one Laplacian has one zero eigenvalue and the other is positive minus sign, those eigenvalues becomes negative. So the solution will escape to the null space, which is 1, 1, 1, 1, if you remember our example. And if you take the Laplacian matrix and multiply it with one's vector, you get zero, which makes sense because this is your eigenvector, this is your zero eigenvalue. And if you take a system matrix multiplied by the eigenvector that corresponds to zero eigenvalue, you get zero. Okay, so two more examples. The first example is intentionally undirected, and the second one is directed because, yes, we have some undirected arrow, but you only need one. Whenever your graph can have hundreds of undirected edges. If you only have one or more directed edges, then the total graph is directed graph. So let's first write the Laplacian matrix for the undirected case. First first degrees. Agent one has degree of one neighbor. Two has two neighbors. Three has one neighbor. So 1, 2, and 1. Agent one communicates only with agent two. Agent two communicates with 1 and 3 communicates with 2. That's the Laplacian. It is symmetric since the graph is undirected and connected. But now we have a directed case. Let's see what happens for directed case. First of all, this information exchange is undirected, so agent one has one neighbor and agent one receives information from second one. Now let's look at second one. Second one receives information from the first one. So my degree, I have one neighbor that I'm receiving information, which is number one. Now, the third agent, agent two, does not receive information from third agent, so its degree is one. It only receives information from one of the agents, which is one. That's why your degree is one. Now, if you look at agent three receives information from agent two, so its degree is one. So unlike the undirected case, when you have directed case, these are the changes. And more importantly, if you look at L does not equal to its transpose. Simply, if you take its transpose, you know, you are going to get the first, if you just look at the first row, it will be 0, 0, 1 instead of 1, minus 1, 0. So it won't be symmetric. And it is generally, L is not symmetric for connected and directed graphs. And there are a couple of properties, like the first eigenvalue is again 0, and it again corresponds to the null space or the eigenvector of ones. All other eigenvalues, the real part of all other eigenvalues are positive, because when you have directed graphs, they can have complex eigenvalues. When you have undirected graphs, since L equals to L transpose, all the eigenvalues are real. But for the case of directed and connected graphs, you can have complex eigenvalues. That's why we look at the real part as opposed to just the eigenvalues for the undirected case, which are already real. So, all right, so real part of the second smallest eigenvalue, once again called the algebraic connectivity or Fiedler eigenvalue, which I prefer. Again, you have L, one multiplication gives 0 because of this eigenvector that corresponds to the 0 eigenvalue of this Laplacian. And the first eigenvalue is 0, as we just mentioned, and it is simple when the graph is subject to spanning tree. So for directed graphs, we it is off right now. Common standard to assume that the graph is subject to a spanning tree because of how information flows, and in this case, you are only going to have one zero eigenvalue for connected and directed graphs. So I will explain spanning tree in this example. So spanning tree, if I define, is nothing but it ensures each node, each agent receives information directly or indirectly from the root or leader nodes. Okay. So there are some nodes that we are going to call as the leader nodes, leading nodes, or root nodes. Information must start there. And this particular notion will be important when we look at leader-follower networks. But for now, let's see which agents can be root agents so that information flows to all agents either directly, indirectly. For example, if agent 1 is the root agent, then this is information flows between 1 and 2 to 1. So that information comes to here. There is an arrow, goes there to agent 3. It goes to agent 4 and comes back. So if agent 1 is the basically root agent, information flows to all agents. So it can be a root agent. Likewise, the second agent. If second agent is the root, it can send information to 1, 3, and 4. But in this case, for example, 3 cannot be a root node because it cannot send information to 2 or indirectly to 1, so it cannot affect the upper portion of the graph. So 3 and 4 cannot be root nodes in this case. So this graph, if the root node is 1 or 2 or both, yes, then it satisfies the spanning tree consideration. Now let's look at this graph. Change a little bit. In this case, 1 cannot be the root node because simply it cannot send information to 2 or 4. It is impossible to reach 3 anyways. Agent 4, can it be? No, it sends information to 1, but that information is got blocked at 1. It never reaches to 2 or 3. So in this case, 1 and 4 cannot be the root nodes. But if you look at 2 or 3, same. I will just pick 3. If 3 is the root node, information flows here and there. And indirectly, since there is a undirected path, 3 sends information to 2 and 1. So if agents 3 is the root agent, information flows everywhere. Likewise, agent 2. Now, in this case, agent 1 is the only one that must be root node to satisfy the spanning tree consideration. If information starts from here, it goes to agent 2. If it goes to agent 2, it comes to 3, 4, and from 4 to 2. So if this is the root node, information flows everywhere, directly to number 2 and indirectly to number 2, and number 3 and number 4. So if you have to undirected graph, you don't need to consider a spanning tree consideration because anyone can be the root agent. It doesn't matter. So since it's arbitrary, we don't impose spanning tree consideration to undirected graphs. For example, agent 4, it can send information to 2, 3, 3 to 2, 2 to 1. Since these are all undirected paths, information flows everywhere seamlessly. But that's why it is important to have the zero eigenvalue of directed connected graph to be simple. So that's why we impose this spanning tree consideration. And I hope those examples, 3 examples, tell you clearly which nodes can be root nodes for the case when we have spanning tree consideration. Later, this is a heads up. For undirected graphs, for consensus type of dynamics, the role of root agents is not necessarily very important, but when we look at the synchronization and leader-follower roles, I mentioned when you have leader-follower, there are external entities like the external commands interacting with your multi-agent system. In this case, those interactions must be through root nodes or the leader nodes, such that agents flow from all these root nodes to the remaining agents directly or indirectly. So we will use for leader follower networks, we are going to choose leaders from the set of these root or leader nodes. All right. Thank you. See you in next class.